Using a correction factor of 1.5 for USE and 1.4 for THHN in ambient temperatures of 21 to 25 degrees Celsius is acceptable when performing ampacity calculations where the average ambient temperature is 24 degrees Celsius. The correction factor is applied to adjust the ampacity of the conductor to account for the higher ambient temperature. By using this correction factor, one can ensure that the conductors will not exceed their rated temperature limit, even in elevated ambient temperatures. Here's how the correction factor is applied. For USE, with a correction factor of 1.5, the ampacity of the conductor is multiplied by 1.5. For THHN, with a correction factor of 1.4, the ampacity of the conductor is multiplied by 1.4. For example, if the ampacity of a conductor is 100 amps at 25 degrees Celsius, the ampacity at 24 degrees Celsius would be calculated as follows. For USE, it is 100 amps times 1.5, which equals 105 amps. For THHN, it is 100 amps times 1.4, which equals 104 amps. It's important to note that the correction factor is only applicable within the specified ambient temperature range. Outside of this range, the ampacity of the conductor should be adjusted using the appropriate temperature correction factors found in the relevant electrical codes and standards. Using the correction factor in ampacity calculations will help ensure that the electrical system is safe and operates within the intended parameters. It is always best practice to refer to the latest edition of the National Electrical Code, specifically Table 310.16 and related tables and notes, to ensure accurate and compliant ampacity adjustments. Understanding the principles behind ampacity correction is essential for electrical engineers and designers to ensure the safety and reliability of electrical installations. Factors such as ambient temperature, conductor bundling, and conduit fill can significantly impact the heat dissipation capabilities of conductors, and therefore, their current carrying capacity. It is crucial to apply these correction factors diligently and accurately to prevent conductor overheating, insulation degradation, and potential fire hazards. In addition to temperature correction factors, dating factors may also need to be considered. Dating factors account for situations where multiple current-carrying conductors are bundled together or installed in close proximity, which reduces their ability to dissipate heat effectively. These factors are typically found in tables within the NEC, such as Table 310.15. The combined effect of temperature correction and dating factors can significantly reduce the allowable ampacity of conductors, especially in demanding environments. Furthermore, it is essential to consider the specific characteristics of the conductors being used, such as the insulation type and temperature rating. Different insulation types have different temperature ratings, which directly impact their ability to withstand elevated temperatures. For example, THHN conductors are rated for higher temperatures than some other insulation types, which allows them to carry more current in similar conditions. However, it's important to ensure that all components within the electrical system, including terminations, connectors, and equipment, are also rated for the maximum operating temperature of the conductors. In addition to the NEC, other relevant standards and guidelines may provide further guidance on ampacity calculations and conductor selection. These may include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the Insulated Cable Engineers Association, or ISA. Consulting these resources can help ensure that electrical installations meet the highest standards of safety and reliability. Remember that electrical codes and standards are constantly evolving to reflect new technologies, research, and best practices. It is important to stay up to date with the latest changes and updates to ensure that your electrical designs are compliant and safe. Regular training and continuing education are essential for electrical engineers and designers to maintain their knowledge and skills in this rapidly changing field. Moreover, it's crucial to maintain detailed records of all ampacity calculations and dating factors used in your electrical designs. These records can be invaluable for future reference, troubleshooting, and system upgrades. They can also be helpful in demonstrating compliance with relevant codes and standards to regulatory authorities and client By following these best practices and staying informed about the latest developments in electrical engineering, you can ensure that your electrical systems are safe, reliable, and efficient. Ampacity calculations are a fundamental aspect of electrical design, and mastering these concepts is essential for any electrical engineer or designer. Remember to always prioritize safety and accuracy in your calculations, and to consult with experienced professionals when needed. Firstly, the National Electrical Code, NEC, serves as the cornerstone for electrical safety standards in the United States, offering comprehensive guidelines for electrical installations. Secondly, ampacity is defined as the maximum current in amps a conductor can carry continuously without exceeding its temperature rating, ensuring safe and reliable operation. Thirdly, ambient temperature, the temperature of the environment surrounding the conductor, directly affects its heat dissipation capability, requiring adjustments to ampacity calculations. Fourthly, correction factors, as found in NEC tables like 310.16, are multipliers used to adjust the ampacity of conductors based on ambient temperature variations. Fifthly, directing factors address situations with multiple current-carrying conductors in close proximity, reducing their ampacity due to limited heat dissipation. Sixthly, insulation type plays a crucial role, as different materials like THHN have varying temperature ratings that influence their ampacity under specific conditions. Seventhly, conductor size directly impacts ampacity, with larger conductors generally capable of carrying more current, requiring careful selection based on load requirements. Eighthly, voltage drop, the decrease in voltage along a conductor's length, is essential to consider, as excessive drop can impair equipment performance and efficiency. Ninthly, conduit fill, the percentage of space occupied by conductors within a conduit affects heat dissipation, potentially necessitating ampacity adjustments to prevent overheating. Tenthly, safety is paramount, emphasizing the importance of accurate ampacity calculations and adherence to NEC guidelines to prevent electrical hazards and ensure reliable operation. Furthermore, when applying correction factors, it's important to understand the limitations and assumptions underlying the NEC tables. The tables are based on specific conditions such as the type of insulation, the number of conductors in a raceway, and the ambient temperature. If your installation deviates significantly from these conditions, it may be necessary to perform more detailed calculations or consult with a qualified electrical engineer. For example, if you are using a conductor with an insulation type not listed in the NEC tables, you may need to obtain the conductor's ampacity rating from the manufacturer or a recognized testing laboratory. Similarly, if you are installing conductors in a particularly harsh environment, such as a high temperature or corrosive atmosphere, you may need to apply additional directing factors to account for the increased stress on the insulation. In addition to the NEC, other relevant standards and guidelines may provide further information on ampacity calculations and conductor selection. These may include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, the Insulated Cable Engineers Association, or ISA, and the National Electrical Manufacturers Association, or NEMA. Consulting these resources can help ensure that your electrical installations meet the highest standards of safety and reliability. It's also important to consider the impact of harmonics on ampacity calculations. Harmonics are non-sinusoidal currents and voltages that can distort the waveform of the electrical supply. These harmonics can cause increased heating in conductors and equipment, which can reduce their ampacity. If your electrical system is likely to generate significant harmonics, it may be necessary to apply additional directing factors to account for the increased heating. The NEC provides guidance on how to calculate harmonic directing factors in Article 220. Moreover, it's crucial to consider the long-term effects of temperature and humidity on conductor insulation. Over time, exposure to high temperatures and humidity can degrade the insulation, reducing its ability to withstand electrical stress. This can lead to premature failure of the conductor and potential safety hazards. To mitigate these risks, it's important to select conductors with insulation that is specifically designed for the environmental conditions in which they will be installed. For example, conductors with cross-linked polyethylene or XLPE insulation are known for their excellent resistance to heat and moisture. Also, regular inspection and maintenance of electrical systems can help identify and address potential problems before they become serious. This includes checking for signs of insulation degradation, such as cracking or discoloration, and testing the insulation resistance of conductors. By taking proactive measures to maintain your electrical system, you can extend its lifespan and ensure its continued safety and reliability. In addition to the technical aspects of ampacity calculations, it's also important to consider the economic implications of conductor selection. Selecting the appropriate conductor size can have a significant impact on the cost of the electrical installation. Larger conductors are more expensive, but they can also reduce energy losses and improve the overall efficiency of the system. Therefore, it's important to perform a cost-benefit analysis to determine the optimal conductor size for your specific application. This analysis should take into account factors such as the initial cost of the conductors, the cost of energy losses, and the expected lifespan of the electrical system. Furthermore, it's crucial to document all ampacity calculations and derating factors used in your electrical designs. This documentation should be readily available for future reference and should be updated whenever changes are made to the electrical system. Proper documentation can help ensure that the electrical system is properly maintained and operated, and it can also be valuable in the event of a fault or failure. Also, it's important to stay up to date with the latest changes and updates to the NEC and other relevant standards. Electrical codes and standards are constantly evolving to reflect new technologies, research, and best practices. By staying informed about these changes, you can ensure that your electrical designs are compliant and safe. Regular training and continuing education are essential for electrical engineers and designers to maintain their knowledge and skills in this rapidly changing field. And remember, electrical safety is paramount. Always prioritize safety in your electrical designs and installations, and consult with qualified professionals when needed. By following these best practices and staying informed about the latest development in electrical engineering, you can ensure that your electrical systems are safe, reliable, and efficient. Finally, consider the future expansion of the electrical system when selecting conductor sizes. It is often more cost-effective to install larger conductors initially than to upgrade the system later to accommodate increased loads.